Hey guys, welcome to Magnetism video 8. In this video, we're going to take a look at starting to answer the question, why does a magnetic field affect a moving charged particle or a current carrying wire? Why is it only when it's moving that it's affected rather than a static electric charge? So let's get into it. Now, my first observation upon putting a compass around or near a current carrying wire is that when the current begins, the magnetic needle of the compass deflects. This indicates that there is a magnetic field around moving charged particles. What's more interesting and what will become very important is that if you use a series of compasses around the current carrying wire, you'll see that the magnetic field actually wraps around the wire. So if we're looking at the wire head on here with the current either moving into or out of the screen, we'll see that the magnetic field is sort of looping around this wire. Now this becomes very important in using what we call the second right-hand rule, sometimes known as the corkscrew right-hand rule. Now in this right-hand rule, we take our thumb to represent the current direction in the wire and our fingers to represent the magnetic field. Now our fingers can either point clockwise or counterclockwise depending on the direction of the current. So if we're looking at a current carrying wire that has its current directed out of the screen, we would see that we point our thumb pointing out of the screen and our fingers would curve counterclockwise. In the other case, where the current is directed into the screen, we'd see that our fingers would curve clockwise. So what's interesting here, and what is attributed to Michael Faraday, is that the magnetic field lines are not straight lines around the wire. Now, if we had a charged wire that had, say, positive charge attached to it, we would see that the electric field lines would originate at the wire and would radiate outwards. So if we were looking at it in this head-on perspective where the current is, or let's say where the charge is in the wire and the wire is pointing into and out of the screen, whether the charge is moving or not, the electric field is pointing outwards. At the time, the finding that the magnetic field lines were curved was actually a huge point of tension between Michael Faraday and the scientists of the time. They actually laughed at him and ridiculed him for thinking that field lines could curve in such a way. So hopefully at this point, you're starting to see what the reason might be that magnetic fields only interact with moving charges. So let's revisit this example from one of the earlier videos. We have this circuit with this pendulum made of wire, and we have this permanent magnet. Now we see very clearly that there is a magnetic field here from the permanent horseshoe magnet, but when there's no current running through the wire, there's no interaction. The minute I close the switch and there's current moving through the wires, I do see an interaction. In other words, I do see that there's a magnetic force interacting with this current carrying wire. Now at this point, we've established that when charges move, in other words, when I have a current, I have a magnetic field that is generated around those moving charges or around that current carrying wire. Now this magnetic field is independent than the permanent magnetic field. So what that basically means is that the permanent magnetic field is interacting with the magnetic field that is generated around the current carrying wire. So now that we know that moving charges have magnetic fields developed around them, it makes more sense that only when they're moving and they have their own magnetic field would it be able to interact with the other magnetic field. It's almost like I can't understand the language until it's translated into something I can understand. Or perhaps it could go even further and say that language isn't even there until the charge is moving. So just to practice, let's say that I have a wire with a current moving from left to right like this. If I use the second right-hand rule, what I would say is I'll point my thumb in the direction of the current, and I'll see that my fingers curl outwards above the wire and into the screen below the wire. So I'd represent this with dots above the wire and X's below the wire. Now if I flip the direction of the current, I would see that my fingers would point into the screen above the wire and come out of the screen below the wire. This is one common way that we represent the direction of the magnetic field around a current carrying wire. Now, one thing to keep in mind is the difference between conventional current and electron flow. So if I have conventional current pointing to the right, then electron flow would be to the left. Keep that in mind when using the second right-hand rule. Let's take a look though at how these magnetic fields can superposition. In other words, they can overlap if I have multiple wires in their same vicinity. So a very cool phenomenon is that if I have two parallel wires, let's say that their currents are traveling in the same direction, and these two wires lie within a region next to one another. When current actually runs through the wires, I will see the wires interact with one another. In other words, the magnetic fields around each of the wires will interact, either pushing or pulling the wires towards one another. Perhaps a better description of their interaction is repulsion or attraction. So let's analyze the situation in a little bit more detail. It becomes a little complicated because we're going to use both right-hand rules that we've learned so far to analyze this situation. Let's start with both wires have a current directed up the plane of the screen. So if I use my second right-hand rule to begin with, I'm going to draw the location or the direction of the magnetic field relative to each wire as seen from the perspective of the other. So for the wire on the right, what I would say is my thumb needs to point up the plane of the page, and I would see that on the right-hand side of this wire, the magnetic field points into the screen, and on the left-hand side of that wire, the magnetic field is pointing out of the screen. Now if I do the same thing for the wire on the left, I see the same situation. I see that the field is pointing in on the right and out on the left. Now what we're interested to see is how the field of one wire interacts with the field of the other. So here's the part we need to focus on. The wire on the right has a field directed out of the screen at the location where the wire on the left is. And the wire on the left has a magnetic field that's directed into the screen at the location of the wire on the right. So look at the picture to help you understand this. So basically what I see now is that for the wire on the right, it is a current running up the plane of the screen and it is in a magnetic field that's directed into the page. Now that magnetic field is due to the wire on the other side. Now the wire on the left has a current directed also up the plane of the screen, but it's in a magnetic field that is pointing out of the page that is produced by the wire on the right. So now we're going to see that we have a current and a magnetic field direction, so we can see the direction of the force that each wire would experience due to the field of the other wire. So the wire on the right has a current pointing up the plane of the page. It also is experiencing a magnetic field that's pointing into the plane of the page. So now I use my first right-hand rule where my fingers are pointing into the screen. The current is directed up the plane of the page, so my index finger points up, and I see that my thumb is left pointing to the left. So that means that the wire on the right-hand side is experiencing a magnetic force to the left. Now if we analyze the wire on the left, I'm going to see that the magnetic field is pointing out of the plane of the screen at that location, and its current is directed up, leaving the thumb pointing to the right. In other words, the magnetic force of this wire is pointing to the right. So you can see by looking at the force directions of both wires, these two wires will in fact attract one another. That explanation might take 2 or 3 passes in understanding because it is quite complicated in that we're using 2 different right-hand rules. The main idea, though, to keep in mind is that the magnetic field from one wire serves as the field that's causing the force on the other wire because of its interaction with the magnetic field produced by the current. Now let's take a look at when I have 2 current carrying wires, but their currents are running in opposite directions. Go ahead and pause the video and try to explain for yourself what direction each of the forces would point for either wire. So if I take the wire on the right, I see the currents running up the plane of the page, so its magnetic field would be into the screen on the right hand side and out of the screen on the left hand side. Now the wire on the left would have a current pointing down the plane of the screen, so it would have a magnetic field pointing into the screen on the left and out of the screen on the right. This time, if we focus on the magnetic fields that are in the vicinity of each of the wires, I see that the magnetic field of the wire on the right is pointing out of the screen in the location where the wire on the left is located. And similarly, I see that the wire on the right hand side is experiencing a magnetic field produced by the other wire that's also directed out of the screen at the location where the right hand wire is located. This is contrary to what we saw before. In the other case, each wire was experiencing a magnetic field either pointing into or out of the screen, whereas in this case, we see that one is experiencing a magnetic field that's pointing out of the screen, the other is seeing a magnetic field that's also pointing out of the screen, but with a current in a different direction. So now I switch to the first right-hand rule. I see that for the wire on the right, the magnetic field is pointing out of the screen. My current is directed up the plane of the screen, leaving my thumb pointing to the right. Now if I do the same thing for the wire on the left, I see that the magnetic field is pointing out of the plane of the screen. This time, however, the current is directed down the plane of the screen, leaving my thumb pointing to the left. So here you see that both forces point in opposite directions, and thus the wires repel one another. So all the crazy details aside, what we've essentially looked at in this video is the idea of an electromagnet. It's kind of cool. It's a magnet that only exists magnetically when it has electrical current running through it. So what I can do essentially is take, let's say, a nail and wrap a copper wire around it several times, overlapping the field multiple times, and then run a current through that coil, and what I've established is a magnetic field that is now serving as a magnet. In this video, we've really only paid attention to the directions and orientations of the magnetic field around the current carrying wires. In the next video, we're going to take a look at a lot more rigorous detail mathematically how the current strength relates to the magnetic field and how the position away from the current carrying wire affects the magnetic field. We'll also take a look at how wrapping a wire around some sort of central shaft and creating a solenoid actually affects the magnetic field as well. So check back for that.